As you may or may not be aware, humans have 10 fingers, and so we use base 10, or the decimal system, for our numbers, with each digit being a value of 0 through to 9, and each position representing a power of 10. So the number 56 can be broken down as 6 times 10 to the power 0 plus 5 times 10 to the power 1. Sadly, computers were only blessed with 2 thumbs, so they use base 2 or binary. So each digit or bit can either be a 0 or a 1, and each column you move left multiplies the number by 2 to the power of the column. So that 56 above would be 111000, or 2 cubed plus 2 to the 4 plus 2 to the 5. If you want to write out a binary number in Gamemaker, you just prepend it by 0b. There are 6 bitwise operators available: AND, NOT, OR, XOR, and BitShift left and BitShift right. They behave like the logical operators you are used to, but instead of evaluating whole value, they operate on each individual bit. AND operator, this compares 2 values bit by bit and returns 1 only if both bits are 1. The OR operator, which returns 1 if either bit is 1. XOR, or exclusive OR, which returns 1 if just one of the bits is 1 and otherwise returns 0. The NOT operator, this just flips all of the bits, so 1s become 0 and 0s become 1. And the bit shift operators, both left and right. This shifts the bits by a set number, so you can think of it as multiplying or dividing by a power of 2. Obviously, be aware that this is integer division. So, for example, 11 divided by 2 would be 5. So you might be thinking, when would I actually use any of this? One of the simplest use cases, determining whether a number is odd or even. Simply AND the number with 1. If it's odd, it will return 1. Otherwise, it'll return 0. Or, let's say you've got a map where going off one edge brings you back to the other side. If your map is a power of 2, like 128, you can wrap positions using a bit mask instead. So that 127 is basically a mask that keeps the value between 0 and 127. If you instead wanted to stop the player from walking off the edge of a map, or wanted to collide and prevent a player from entering a tile, you can AND the position with the NOT of the tile size, -1, for the left and top edge, and just add the tile size for the right and bottom edge. So while all of that can be useful, in modern game development you rarely need to worry about the performance, basic math operations, unless you're doing something particularly weird. But bit manipulation does have one real power: bitmasking. Instead of thinking of binary as its number representation, you can instead consider it a series of Boolean values. This lets you store multiple true or false values inside a single variable and check all of them at once. So not only is this very performant and memory efficient, but also scales really well and can make your systems much leaner once they grow in complexity. So instead of checking each variable, you can instead check everything in one variable. And to combine them, you just OR them into the original number. So if you want to check if a player has the blue key, for instance, you just take the inventory and AND the blue key flag. And if it is 0, he doesn't have the blue key. Otherwise, he has the blue key. If you want to remove a flag, you just AND the inventory with the NOT of the flag you want to remove. This flips the bit of the flag, leaving all others untouched. So now, let's look at a more complex example. An elemental system with strengths and weaknesses. First, we create an enum. This will assign the values 0, 1, 2, and so on to each value. It means we don't have to manually track which bit each element uses. This means we can add and remove elements in the future without any hassle. Then, each monster will store its type in a single variable. So we just 1 and bit shift left the element enum. As you can see, we are bit shifting the number by 1, which is just a single bit, with the enum value. If a monster has multiple types, You can just add more by ORing more values into it. So now this one variable represents all of the monster's type. Next, for each move, we'll create a mask that defines what it's strong against. For example, for a fire attack, we'll set it to 0. Then we'll OR in 1 bit shifted left by the element grass. And if we want to add in more, we can then OR in 1 bit shifted left by the element bug. If we want to check if a move is effective, we can just do fire effective mask and the monster type mask and check that it doesn't equal 0. This works because the AND operation isolates shared bits. So if the monster has any type that matches the move's effective mask, the result will be non-zero. But what if you wanted effectiveness to stack? For example, if a monster is both grass and bug, and both of those are weak to fire, you might want the damage multiplier to be applied twice. First, we isolate the matching types as above, and do a fire effective mask and monster type mask. Now we just count how many bits are set to 1 using this simple but effective bit of maths. Don't worry about the while loop, it'll only run once for each active bit. In this case, twice, so it's still really fast. Now we just scale the damage based on that count by raising it to the power. If you wanted to handle resistances and immunities that also stack, this would just be the same, and it'd just be a different mask for each one, multiplied at the end.